Hi everyone, and welcome back to Physics with Mr. Simons. Right, again, we're making physics simple by making sure you understand your past exam questions and how we structure and ask the questions and how we vary. Today's lesson, we're looking at November 2015's exam question. What makes this question special? They gave you a table with concentrations and you just have to work straight from the table to get the Kc value. Right, so the Kc value question is a bit easier here, but the theory questions are a little bit more complex. Right, so let's look at the question. Right, question 6. An unknown gas, X2, is sealed in a container and allowed to form X3 gas at 300 degrees Celsius. The reaction reaches keyword equilibrium according to the following balance equation: 3x2 to form 2x3. 2 times 3, 6. 2 times 3, 6. That way we've balanced the equation. So I have 6 moles of X2 and 6 of X3. Now, how will the rate of the formation of X3 compare to the rate of formation of X2 at equilibrium? Write down only higher than, lower than, or equal. Keyword at equilibrium. Say the reaction mixture is analyzed at regular time intervals. The results obtained are shown in the table below. So there you can see they gave you concentration of X2, concentration of X3. Now we've increased our time intervals in increments of 2, 0 plus 2 plus 2 plus 2, all the way till 10. And there for X2, went from 0,4 to 0.22 to 0,08 to 0,06, and there you can see it stayed constant. There's 0 to 0,120 to 0,213, and there it stayed constant, 0.226. Right, and they say calculate the equilibrium constant Kc for this reaction at 300 degrees Celsius. So again, I've broken this exam question up in parts. I didn't want to squash everything on one page. So we're first going to answer this section before we go to the next part of the question. Alright, so how will the rate of the formation of X3 compare to the rate of formation X2 at equilibrium? At equilibrium, they should be equal to each other, right? Formation of that must equal formation of that. Therefore, they've reached equilibrium. Number 6.2, calculate the equilibrium constant Kc for this reaction at 300 degrees Celsius for 4 marks. So at 300 degrees Celsius, we can see here after 6 seconds, we've reached the same answer there. After 6 seconds, reached the same value of concentration. Concentration hasn't increased or decreased. So therefore, X2 and X3, that's my equilibrium concentration, right? So Kc always equals my concentration of my products divided by my concentration of my reactants. So there X32 becomes X3 squared. And there X2 cubed. So 0,226 squared, 0,06 to the power 3. Using my calculator, I get 236,46. So 1 mark there for correct formula for Kc. 2 marks for substitution, correct value on top, correct value at the bottom, and 1 mark for the Kc value. Right, so I hope you follow. I assume you understand. Right, now let's go to the next questions. Now they say more X3 is now added to the container, right? So I think X3 was on the product side, so more products are now added to the container. How will this change affect the amount of X2 gas? Write down only increase, decrease, or remain the same. Then we have to use Le Chatelier's principle to explain now why we chose that answer in question 6.3.1. Second part, they say the curves on the set of x's below was obtained from the results in the table. So there they give a table, concentration and time. So there we can see my reactants concentration decrease, my products concentration increase. How does the rate of the forward reaction compare to that of the reverse reaction? Here at time t1, write down only higher than, lower than, or equal. So generally we look at the gradients at that point. Right, but let's look at the problem, and then we still have another set of questions that's going to come after. Right, so more X2 is added now in the container, or X3, so we've increased this. So according to Le Chatelier, to oppose this increase, we have to increase X2. Right, so how would x2 be affected? It increases. So that there increases, so x3 can decrease. Using Le Chatelier's principle to explain question 6.3, the increase in x3 is opposed. Alright, so to oppose that, that means the reverse reaction is favored. So we use up the x3 that was added extra, right, and that therefore decreases while x2 increases, right? So there, 1 mark for increase, 1 for understanding that the increase must be opposed, and another mark for understanding that therefore the reverse reaction is favored. Now, they want to know how does the rate of the forward reaction compare to that of the reverse reaction, right? In this case, it is higher than, all right? So the rate of the forward reaction and the rate of the reverse reaction at T1, right? So there, forward is my reactants being used up, reverse reaction, products before they reach thing. So at that point there, that rate of the forward reaction has a higher gradient. Therefore, there it's higher than what this one is here. The gradient is greater. Right? So that is higher than. Hope you follow and understand so far. Let's go to the next question. Reaction is now repeated at a temperature of 400 degrees Celsius. The curves indicated by the dotted lines below were obtained at this temperature. So the solid line there is at 300 degrees and the dotted lines are at 400 degrees. Now they want to know, is the forward reaction exothermic or endothermic? Fully explain how you've arrived at this answer for 4 marks. Next question, the Maxwell-Boltzmann distribution curve below represents the number of particles against kinetic energy at 300 degrees Celsius. Alright, they say redraw the curve on the same set of axes. Sketch the curve that will be obtained at 400 degrees Celsius, clearly labeling the curves at 300 degrees and 400 degrees respectively. Alright, so let's go look at the answers or solutions. So 6.5 is the forward reaction exothermic or endothermic. Fully explain how you arrived at the answer. Right, so exothermic, 1 mark. Right, so now you can see there my products. That's how my products were formed initially, the solid line. Then my products there, as you can see, that line went lower. Then I had my reactants, right? And so with increase in temperature, my reactants went higher, right? So I can say the concentration of the products, X3, is lower. And the concentration of my reactants, X2, is higher. I hope you understand what I mean. So this is higher than that, and that is lower than that. The increase in temperature favors the reverse reaction. So why we say reverse reaction? Because my reactants got higher and my products got lower. So my products were used up and more reactants were formed. So the increase in temperature favored the reverse reaction. Now, according to Le Chatelier's principle, an increase in temperature always favors a endothermic reaction. So if my reverse then is endothermic because it increased, then my forward reaction must be exothermic. So reverse reaction is endothermic, then my forward reaction is exothermic. So hope you follow, that makes sense to you. So my products became less, as you can see there, right? And my reactants became more. Right? So the reactants, that line is higher than this, but the products is lower. Now they say redraw the curve on the same set of axes, sketch the curve that will be obtained at 400 degrees, clearly labeling the curves at 300 degrees Celsius and 400 degrees respectively. So number 1, the peak would be lower, alright, with the increase in temperature. But yeah, if we look at the kinetic enough particles that have enough kinetic energy to partake in the reaction, we draw a line there. The area for the 400 degrees Celsius would be greater than the area for 300 degrees Celsius. So there's your second mark for showing that that area with kinetic energy is greater. Alright, so hope you follow, understand. I wish you nothing but the best. Continue practicing. God bless. Bye.